Today I will talk about the acid and base theories. After the theories, I will also mention the pH and pOH. I will solve some problems. Okay, firstly we have three theories, but I want to firstly show Arrhenius acid-base theory and Lewis acid-base theory. Arrhenius acid-base theory is very simple. If something ionizes and gives proton, then it is an acid. And if the material gives the OH ions, if it ionizes, then it's called as base. So the most simple example is sodium hydroxide. So if you put the sodium hydroxide in water, it ionizes as sodium plus ions plus the hydroxide ion. And due to the hydroxide ion, we called that sodium hydroxide is a base. So this is the Arrhenius base, and we can give another example, acetic acid. So again, if we put that chemical in water, it ionizes and it produces a proton in water, so that this chemical is an acid. And Lewis acid-base theory is a little bit more complicated, I think. So electron donors are called as base, and electron acceptors are acids. Again, we can give an example to simplify the concept. For instance, we can think an ammonia molecule and it has 2 electrons. If you put it in water, and water has this kind of band structure, and these electrons attach to the hydrogen, and the electrons goes to the oxygen side and it produces OH minus plus NH4 plus ions. So NH3 in this case donated its electrons, therefore it is a base. And water accepted electrons, therefore it behaves like an acid. So this is the Lewis base theory. But today I will go on the conjugated acid-base theory, or it is also called as Bronsted Lowrey theory. In this theory, we have conjugated acids and bases. So again, I want to give an example. So acids, what is acid? Acid is something that donates proton, and base is the something that accepts proton. And we have conjugate acid-base pairs. When an acid donates a proton, it becomes its conjugate base, and when a base accepts a proton, it becomes its conjugate acid. And I can give very simple example again. So think acetic acid, and if we have a water, there's equilibrium reaction. So we produce acetate ion plus H3O plus So here acetic acid gave its proton, so it is an acid, and it creates the conjugate base. And water behaved like a base here, right? This is a base, and it created its conjugated acid. Water is a base here since it accepted a proton. So this is a proton acceptor. Therefore it is a base. And acetic acid is a proton donor. Therefore it is acid. And I can make another example by using a weak base. I think I can use ammonia in this case. We put the ammonia in water. There's an equilibrium reaction. It creates NH4 plus and OH minus ions. So NH3 accepts proton, NH3 accepts proton, therefore this is a base, and NH4 plus becomes its conjugate acid. Water behaved as an acid since it donated its protons, so it is acid in this case, and therefore OH minus ion is the conjugated base. So water is a very different molecule, and water can act as a acid or as a base, and you will see in the next chapters of this video. And water functions as a base in reactions with acids, and it functions as an acid in some reactions. And we have to know the ionization of water. So water ionizes. Think a water molecule in a liquid form. If it ionizes, it creates hydrogen plus, aqua plus, hydroxyl radicals. And we can write a equilibrium expression for this reaction, which is OH minus times hydrogen plus. As you remember from my previous videos, we can't include the liquids in the equilibrium expressions, so I will not write the H2O in this expression. So this expression is also called as Kw, or ion product constant, and Kw equals to OH minus times hydrogen plus concentration. We can look at the reaction in a different way, I think. Think as a two water molecules. We have two water molecules. I'm using the Levi-Strauss structure. I have another water molecule. It's an equilibrium reaction, and I thought that these electrons attach to the hydrogen, and the electrons on the solder molecules goes to the oxygen side and creates hydroxyl radical. And this molecule becomes H3O plus, and this is the acid here, and this is the base, right? And Kw can be written as H3O plus times OH minus. So this is completely the same thing with the H plus times OH minus. And this expression value is 1 time 10 to the minus 14 at room temperature or 25 Celsius. And this value of course change with the temperature. It has a temperature dependence, but we generally use this value to solve the questions. And I want to make an example. The concentration of OH in a solution is 0.0030 molar. Calculate the hydrogen plus ion concentration. So as I know, Kw value is equal to hydrogen plus times OH minus, and it is equal to 1.0 times 10 to minus 14. And we know the OH concentration in this case. I will just write the numbers, and this value is equal to 1.0 times 10 to minus 14, and the hydrogen ion concentration will be equal to 1.0 times 10 to minus 14 over 0.0030, and we can make the calculation, I guess. 10 times 10 to the minus 14 over 0.003. So it is 3.33 times 10 to the minus 12 molar. So as you see, the issue in here, hydrogen plus concentration is very low, and it is not a useful way, I think, right? And a scientist in 1909 proposed a useful solution to deal with low concentration, and he defined a negative logarithm of hydrogen ion concentration, and it's called as pH. So pH is simply minus log of hydrogen plus concentration. But what is the logarithm? So I want to show the function itself. So we have x and y coordinates, and log x is something like this. So at 1, when x value is 1, it becomes 0. And as we said, pH is equals to minus log hydrogen plus concentration. And we can also define another thing, OH ion concentration, and it is minus log OH minus concentration. So if the pH is 7, it means that hydrogen ion concentration is 10 to the minus 7. And it is a natural solution. But if pH becomes 5, for instance, then it is acidic. And if it is 8 or a higher value than the 7, it's a basic solution. But if you look at the function, can pH becomes less than 1? The answer is yes, since if the x value becomes more than 10, for instance 15, then the minus log 15 becomes something minus something. So pH value can be minus. And this is valid for the concentrated strong acids. So just keep in mind that this is a little bit extra information maybe right now, but it is important. So pH is generally defined between 1 to 14, but the values can little exceed this range. And there is a relationship between the pH and the pOH, and it is equal to 14. And if we want to define the OH concentration, it is simply 10 to the minus pOH. Why? Since pOH is equals to minus log OH minus concentration, and we have a 10 here, you know. Firstly, we put the minus side to here, or we multiply the both sides with minus 1, and this value, this thing becomes minus pOH, and we can send the 10 to other side, and OH concentration becomes 10 to the minus pOH. And the same thing can be used for the hydrogen, and the hydrogen concentration will be equal to 10 to the minus pH value. And we can make an example. So calculate hydrogen plus concentration if collected rainwater pH is 5.23. So as I mentioned, pH is minus log hydrogen plus concentration, and this is equal to 5.23. So logarithmic hydrogen plus concentration will be equal to minus 5.23, and hydrogen plus concentration will be 10 to the minus 5.23, and I can calculate this value. And it is equal to 5.89 times 10 to the minus 6 molar. And we can calculate the pOH, since we know the pH plus pOH is equal to 14, right? Or OH times hydrogen ion concentration is equal to 10 to the minus 14. And we know this from the Kw. So if the hydrogen plus concentration is 5.89 times 10 to the minus 6, OH concentration can be found easily. And I want to calculate this value for just an example. And OH ion concentration is 1.7 times 10 to the minus 9. And pOH equals to minus log 1.7 times 10 to the minus 9. And minus log 1.7 times 10 to the minus 9, and it is 8.7. So what will we see if we add them, these two numbers? It will be 14, and the pOH plus the pH is 14. And this example proves the concept basically. And the strength of the acids and bases also different from each other. So we have weak acids and the strong acids. And strong acids are strong electrolytes. They nearly ionize completely in water. And most of the strong acids are inorganic compounds. And we can make a few examples. For instance, HCl, which is a very, very common chemical in the chemistry labs. If you put it in water, it completely ionizes and it creates H3O plus and the chlorine minus ions. And these ions are extremely weak bases. Therefore, these acids are strong. And we have other type of acids, for instance, polyprotic acids. These acids have more than one proton, and the H2SO4 is the most common one. If you put it water, it ionizes and creates the ion and HSO4 minus ion. This is also an acid and it ionizes again in water and creates SO4 2 minus ion in the water. So these are the in aqueous phases, and water here is liquid. So same thing is valid for the bases. So I will talk about the bases here, strong bases. And strong bases are also strong electrolytes. And sodium hydroxide is an example. It's a solid in the room temperature. It's solid. And if you put it water, it creates sodium plus ions and the OH minus ions. And potassium hydroxide is also a strong base. It creates potassium ions and the OH minus ions in water, and they completely ionizes. So when it completely ionizes, it creates lots of ions. And we can make an example. Calculate the pH of 2.5 times 10 to minus 3 molar HCl. So this is a dilute HCl, by the way. Dilute HCl solution. And also calculate the 0.045 molar of this strong base. So we will use ice table to make the calculation. So we have HCl. It ionizes hydrogen plus chlorine minus in aqueous phase. So at initial we have 2.5 times 10 to minus 3 molar HCl. We don't have a hydrogen plus ion or the chlorine, and there will be change. So it completely ionizes. So we deplete all the HCl and we create same amount of hydrogen plus chlorine ions. And we add them up. Equilibrium. Therefore this is called as ice, right? So HCl concentration becomes 0. Hydrogen plus concentration becomes 2.5 times 10 to minus 3 molar. And chlorine concentration becomes plus 2.5 times 10 to minus 3 molar. And pH of the solution is equals to minus log hydrogen concentration, which is 2.5 times 10 to minus 3 molar. And we can calculate this value. Minus log 0.0025. So there are 3 zeros, and it is equal to 2.6. And the same thing can be done for the base. I will make it smaller to gain space here. I will make the ice table for this molecule. We have to write the reaction correctly. And concentration of this base is 0.045. We don't have barium 2 plus at the initial and OH. It completely ionizes, right? So we create barium 2 plus and 2 times hydroxyl. This is important. And at equilibrium, OH concentration becomes 0.090 molar. And pOH is equals to minus log 0.090 minus log 0.090. It is equals to 1.05. And you know that pH plus pOH is equals to 14. In this case, pH becomes 14 minus 1.05, and it is equals to 12.95. And this is the pH of the base solution. And I will talk about the weak acids and weak bases. And in this case, I will consider a monoprotic weak acid, HA. So we have a HA in aqueous solution. We have water again, and there's equilibrium reaction. So it creates H3O plus ions plus the A minus ion in water. So in this reaction, we can write the equilibrium expression, for instance, Kc. And it should be H3O plus times A minus over HA. So water is liquid phase. It shouldn't be in the equilibrium expression. Just a reminder. And also we can write the same reaction in this form. So Kc can also be written as H plus concentration over the A minus times A minus over the HA concentration. So both of them is correct. And we call these cases actually Ka. And the Ka is acid ionization constant, and it is used to define the strength of the acids. If Ka value is larger, then it's a stronger acid. And we can also make the same thing for the weak bases. So for instance, we can think a weak base, ammonia. We put it to the water. Water is liquid, there's a equilibrium reaction again. We create NH4 plus ions plus hydroxyl radicals. So we can write the Kb value. It is NH4 plus times OH minus over the NH3. But now I want to make something different. This is a conjugate acid, right? And can I write the reaction for the conjugate acid? Since it should give the proton, right? So it can react with water. Water is liquid. This is in the aqueous phase. There will be an equilibrium reaction. It produces ammonia and it creates H3O plus or a proton, but doesn't matter in this case, I think. And I can write a Ka value for this molecule. So it should be NH3 times H3O plus over the NH4 plus. What happens if I multiply Ka and Kb for these two reactions? Let's do it. Ka times Kb. It's equals to Ka. So I will copy this. I will paste here. And I will copy the Kb value. Copy and paste. So if we multiply these two, NH3 cancels, NH4 cancels, and Ka times, 1 second, Yes, NH4 cancels, and Ka times Kb becomes H3O plus times hydroxyl radical. So we learned very important things. Ka times Kb is equal to H3O plus times OH minus ion concentration. And this value, if you remember from the beginning, is equals to Kw. Wow. And what we know also, just a summary, pH plus pOH equals to 14, and the pH equals to minus log hydrogen plus concentration, and the pOH was equals to minus log OH minus concentration. So I want to make a last example, a little bit harder one. So what is the pH of 0.40 molar ammonia solution if Kb value is 1.8 times 10 to minus 5? So again, I want to create a ice table. So initially we have 0.40 molar ammonia. We don't have other ions, and the water is liquid, so I don't have to care. And the change will be minus x. I will produce to plus x for each ions. I will add them up. So it is 0.40 minus x. This is plus x, this is plus x. And I will write Kb. So Kb is NH4 plus OH minus over the NH3, right? And in our case, it is x times x over the 0.40 minus x. So this value, x times x over 0.40 minus x, is equals to x squared over 0.40 minus x, and it is equal to 1.8 times 10 to the minus 5. So here we can cancel the x, but I will not do that to show the solution method of the quadratic equations. So I will multiply these two values to make a small rearrangement. Okay, I will distribute these two numbers. So x squared will be equal to 7.2 times 10 to minus 6 minus 1.8 times 10 to the minus 5x. I think x should be big here, or not to make confusion. I know this value since I have already made the calculation. I just want to make it fast since this video became very long. So as you know, delta equals to b squared minus 4ac, and we can calculate. So here b is this value or we should first make it simple. Minus 7.2 times 10 to minus 6 it equals to 0. So in this kind of equation we have a 1 here, right? This is A, this is B, and this is the C value. So delta equals to B square minus 4AC, and we can simply calculate it. B is 1.8 times 10 to minus 5 square minus 4, A is 1, and C is minus, so this becomes plus 7.2 times 10 to the minus 6. So this value equals to 2 times 8 times 10 to the minus 5. And we know that x12 equals to minus b plus minus kök delta over 2a. So here our delta value is this, but we need a square root of delta, which is equal to 0.005317. And I want to calculate x here, and x will be equal to 1 of x at least, 1.8 times 10 to the minus 5 times square root of delta, which is this number, and this is plus or minus. Over 2a, or 2 times 1, and if you calculate it, it will become 0.00267. What about x2? So in x2, so this is x1, so in x2 this becomes minus, and this number is bigger than this one, so x2 will be definitely smaller than 0, and which is not possible, since if x is smaller than 0, then the OH minus concentration becomes less than 0, and this is not reasonable. So we have only one correct answer, and which is this. This is the concentration of the OH, and I can calculate the pH, since the pH will be equal to minus log x, and the x is the simply OH ion concentration. Oh, sorry, pOH. So pOH will be equals to minus log 0.00267, and it is equals to 2.57, and the pH will be 14 minus 257, which will be equal to 11.43. So this is the pH of this solution. And if you have questions, you can write comments. If you want to learn specific subjects, you can also write in the comment section. And thank you for your attention.